Hello everyone, I am Professor Shuai Liang at Beijing Forestry University. Today we are going to learn about the wastewater treatment performance and the effluent quality of the MBRs. In this section, we will first learn about the removal performance of MBRs for ordinary pollutants. Then we will learn about the hygiene water qualities of the MBR effluent, where we will know the unique advantages of the MBRs in removing pathogenic microorganisms. Then we will learn about the removal performance of the MBRs for emerging pollutants. At last, we will learn about the development potential of MBRs in energy recovery. First is about the ordinary pollutants removal by MBRs. The ordinary pollutants typically include organic matter, ammonium nitrogen, total phosphorus, suspended solids, and turbidity. The organic matter was usually quantified in terms of chemical oxygen demand, short for COD, or biological oxygen demand, short for BOD. The required treatment efficiency for these pollutants is usually different, depending on the effluent wastewater type, effluent demand, and the corresponding specific treatment standards. For example, the treatment efficiency required for municipal wastewater and industrial wastewater can be different. Besides, the treatment standards will be much higher if the wastewater is treated for reuse purpose than for discharge purpose. And also, the specific treatment standards adopted in different countries are different. That will lead to different treatment requirements. There are many different configurations of the MBR process. The primary version of MBR is a simple combination of the aerobic unit and the membrane tank. It can be named as OMBR, and it can be used to effectively remove COD, BOD, ammonium nitrogen, and SS. The first wave of full-scale MBRs, which were established in the 1990s or 2000s, were mainly in the form of OMBR. For the total nitrogen removal, denitrification is required, and therefore, an anoxic zone should be added before or after the aerobic tank. That forms an anoxic aerobic MBR process, which can be named as AOMBR. For simultaneous removal of the nitrogen and phosphorus nutrients using a biological method, an anaerobic zone is further added to trigger the microbial phosphorus release and uptake mechanism, and forms an anaerobic, anoxic, aerobic MBR process, which can be named as AAO-MBR. The AAO-MBR process is the most prevalent process in large-scale MBR-based plants for municipal wastewater treatment. By the way, the detailed arrangement of the zones can differ according to the specific design of the process flow. For municipal wastewater treatment, a literature survey of the treatment efficiencies of COD, ammonium nitrogen, and total phosphorus in full-scale municipal wastewater MBRs is given in this figure. We can see the survey shows that the effluent concentrations of COD, ammonium nitrogen, and total phosphorus were mainly in the ranges of 500 to 700, 25 to 50, 40 to 70, and 6 to 12 mg per liter, respectively. The effluent concentrations of COD, ammonium nitrogen, and total phosphorus were mainly in the ranges of 10 to 30, 0 to 3, 5 to 15, and 0 to 1 mg per liter, respectively. An average rate of about 95% was achieved for COD and ammonium nitrogen removal. Although with a larger fluctuation, the total nitrogen removal rate mostly reached 80% to 90%. The total phosphorus removal rate varied from 80% to 99%, depending on the biological status and the chemical dosages into the process for total phosphorus removal. Compared with conventional activated sludge processes, MBR is particularly effective in the removal of SS, COD, and ammonia nitrogen. As for biological nutrient removal, MBR is also competitive for total nitrogen removal. But for total phosphorus, chemical precipitation is sometimes required to assist in further removal of total phosphorus. Overall, we can see that the MBR process is extremely suitable for municipal wastewater treatment. The application of MBR has also been extended to industrial wastewater treatment. This table shows the representative large-scale MBR projects for industrial wastewater treatment in China since 2015. An increasing number of MBRs have been applied to treat a variety of industrial wastewaters. The pollutant removal efficiencies vary largely according to the wastewater type. MBR has even been applied for full-scale leachate treatment. As we can see in this figure, the capacity of full-scale MBRs for leachate treatment in China has been increasing, and a recent survey shows that the MBR units can achieve more than 90% of BOD and COD removal and over 95% of ammonia nitrogen removal. Further research and development are definitely worthwhile. There are several technical advances of MBR to support its excellence in ordinary pollutant removal, and that correspond to different removal mechanisms. Firstly, these membranes can directly reject sludge blocks, microorganism cells, and other suspended solids larger than 0.5 micrometer. Besides, after a certain operation period, the membrane pores will be narrowed due to adsorption or blocking of effluent, or the membrane surface is covered by a dynamic effluent layer. This consequently can enhance the rejection ability of the membranes, thereby enabling the partial rejection of biopolymer clusters and debris, colloidal, COD, nitrogen and phosphorus, and even soluble substances such as SMP and some less biodegradable solutes. We know that the microfiltration or ultrafiltration process is a physical process, and it is not likely to straightforwardly change the nature of the microorganisms in the MBR tanks. However, it can profoundly enhance the biological process due to complete retention of the microorganisms and partial rejection of the pollutants. The complete separation of hydraulic retention time (HRT) and the sludge retention time (SRT) enables MBR to maintain a high sludge concentration and a low food-to-microorganism ratio (F/M ratio). That means the sludge loading is lower in MBRs. Therefore, the microorganisms can be more readily kept in the endogenous respiratory period for more thorough degradation of the pollutants. For municipal wastewater treatment, the sludge loading of MBR is typically in the range of 0.03 to 0.1 kg BOD5 per kg MLSS per day. This is lower than that of conventional activated sludge, which is normally 0.05 to 0.15 kg BOD5 per kg MLSS per day. Moreover, the co-retention of microorganisms and pollutants is also conducive to microbial activities for the removal of refractory pollutants. Again, due to membrane rejection, nitrifying bacteria are easier to enrich in the system and become more resilient at low temperatures, which is important to the stable removal of ammonia nitrogen and beneficial for overall total nitrogen removal. For biological phosphorus removal, MBR acts like a double-edged sword. On the one hand, MBR can possess a high sludge concentration and a high phosphorus content per unit mass of sludge, and the membrane can reject some of the colloidal phosphorus as well. On the other hand, the typically longer sludge retention time, or MBR, means a slower discharge of the excess sludge for the system, and the chemical removal of total phosphorus by aiding precipitants or coagulants is sometimes needed to guarantee the effluent quality. It is noteworthy that aiding precipitant or coagulants also has the merit of alleviating membrane fouling. From the operation perspective, due to the complete rejection of biomass by the membrane, the MBR system is more resistant to sludge bulking problems, which usually trouble the conventional activated sludge processes. In addition, the microorganisms in the MBR are more adaptable in unstable environments. Compared with the conventional activated sludge process, a more stable operation and pollutant removal may be achieved by MBR in cases of high-strength wastewater, frequent shock or effluent quality, fragile microbiota, or unstable ambient conditions. Moreover, MBR is more flexible in process configuration, easier for modularized installation, or more convenient for automatic operation. These provide MBR with additional opportunities for applications in the areas of, for example, specific industrial wastewater treatment, decentralized wastewater treatment, such as in rural areas, and anaerobic processes, such as NMBR. Let's continue to look into the hygiene water quality of the MBR effluent. The presence of pathogens is of primary concern in wastewater reclamation and reuse for the purpose of, for example, lavatory flushing, vehicle washing, urban greening, recreational environmental reuse, and farmland irrigation. Pathogens that affect hygiene water quality cover a wide range of protozoa, helminths, fungal spores, pathogenic bacteria such as fecal coliform and enterococci, and viruses such as enterovirus, adenovirus, and norovirus. The health risks due to direct or indirect human exposure to these pathogens should be seriously considered when designing wastewater reclamation processes. Fecal coliform is usually employed as an indicator of pathogenic bacteria in wastewater reclamation and reuse standards. It is noted that pathogenic bacteria are also subject to wastewater discharge standards due to their profound risks to the ecosystems and public health. F-specific coliphage, somatic coliphage, and phage T4 are often employed as indicators of viruses in MBR research. The left figure shows a comparison between the sizes of membrane pores and different pathogens. It is clear that the microfiltration or ultrafiltration membranes can effectively reject protozoa, helminths, fungal spores, and bacteria because they are larger than the membrane pores. This figure shows a comparison of the removal efficiencies of bacteria and viruses between the full-scale MBR and conventional activated sludge plant. As shown in this figure, a survey of full-scale wastewater treatment plants shows that the log removal of E. coli and enterococci by MBR was about 3 orders higher than that by conventional activated sludge. However, unlike the obvious rejection of bacteria by the membrane by steric exclusion, the rejection of viruses is not certain because the sizes of the viruses are comparable or even smaller than the membrane pores. As shown in the right figure, the full-scale MBRs achieve a 3 to 6 log removal of the tested viruses, which are much higher than the conventional activated sludge plants. The conventional active sludge plants only achieve a 1 to 3 log removal. The removal mechanisms of viruses are complicated and have not yet been fully understood. There are several explanations in the literature. A prevailing one is that the membrane and the gel or cake foulant layer together act as a composite filter in tandem to achieve increased rejection of viruses. Firstly, the membrane itself can partly reject viruses, with the rejection rate depending on the pore size. Secondly, the pore channels can be narrowed due to adsorption of effluents onto the pore walls. The gel layer is a matrix of biopolymers with high porosity and water content but very low permeability, and it is compressible and becomes denser at higher transmembrane pressures. The effective pore size of the calcium alginate gel layer is estimated to be 5 to 30 nanometers. The gel layer can contribute largely to the overall rejection of viruses. It should be noted, however, that overgrowth of the gel layer exacerbates membrane fouling. In addition, the viruses can attach to the suspended solids in the mixed liquor, or be entrapped into the sludge flux and be rejected by the membrane. Microbial inactivation of the viruses in the sludge mixed liquor is also a possible mechanism for the removal. And compared with chemical disinfection technologies such as chlorination, UV radiation, and advanced oxidation, membrane-based rejection of the pathogens is a gentle physical process that bypasses the risks of disinfection byproducts, germ resistance, and involuntary mutations. Emerging pollutants or trace organic pollutants have raised public concerns for water safety. These pollutants can exert acute or chronic toxicity even at trace concentrations, and are usually persistent or pseudo-persistent in the aquatic environment. So the occurrence of emerging pollutants in the effluent or wastewater treatment plants should be seriously considered, no matter whether the effluent are to be discharged or reused. The most widely investigated trace organic pollutants, TROPs, includes endocrine disrupting compounds, EDCs, and pharmaceutical and personal care products, PPCPs. They are categorized according to the impact and usage. EDCs includes a range of phenolic compounds and steroidal estrogens. PPCPs can be classified according to their medical effects into anti-inflammatory and analgesic drugs, antibiotics, lipid-regulating drugs, masks, among others. The individual concentrations of the known EDCs in the municipal wastewater typically range from 1 nanogram per liter to 1 microgram per liter. The individual concentrations of detectable PBCPs are usually 10 nanogram to 10 microgram per liter. It is noteworthy that the pollutants listed here are just the tip of the iceberg. There are far more TROPs yet to be properly monitored and unveiled. The removal efficiencies of EDCs and PBCPs in full-scale MBRs is shown in the figure. About half of the TROPs exhibited a high removal rate of over 95%, and two-thirds of them over 80%, whereas a few PBCPs are lower than 20%. The large variability in the removal performance was attributable to the widely varied biodegradability and hydrophobicity. Both of them stem from the chemical structure of the compounds. So, what might happen when the emerging pollutants enter an MBR system? The emerging pollutant in the MBR system may undergo adsorption, degradation, rejection, and evaporation. The first is adsorption. Pollutants can be adsorbed by the bacterial cells, EPS, suspended solids, and colloids in the mixed liquor. The adsorption is mainly determined by the hydrophobicity of the pollutants. After being adsorbed into the sludge phase, the pollutants may then undergo biodegradation, and the two-step process can be described by a two-phase fate model, where the sludge-water partition coefficient, water-sludge mass transfer rate constant, and the biodegradation rate constant are the key parameters. In addition, the adsorption may be strengthened by adding adsorbents such as powdered activated carbon into the MBR system. The membrane will guarantee complete rejection of the adsorbent particles, Note that adsorption is merely a physical process that transfers the TROPs from the aqueous phase to the sludge solid phase. Ultimate removal of the pollutants still relies on degradation or proper disposal of the excess sludge. For TROPs that are neither adsorbable or biodegradable, advanced treatment such as ozonation and nanofiltration is incorporated into the system to ensure high quality of the effluent. TROPs may undergo biodegradation after being adsorbed. The second is degradation. For TROPs which are readily degradable, the removal efficiencies by MBR and conventional activated sludge are normally comparable, whereas for refractory TROPs, the MBR is more effective in biological degradation. This can be attributed to the adsorption of TROPs by sludge and EPS and the membrane interception of MBR. For TROPs with strong hydrophobicity that are readily adsorbable by the sludge, the higher sludge concentrations as well as probably higher EPS content in the MBR are conducive to the TROP's uptake. But the longer SRT is unfavorable for the discharge of excess sludge. For TROPs with weaker hydrophobicity but still adsorbable by the particles and colloids in the mixed liquor, the MBR is advantageous in rejecting these chemicals and improving the effluent quality. Overall, the removal efficiencies are jointly influenced by the mixed liquor properties and the operational conditions. In short, the removal efficiencies of TROPs are mainly dependent on their biodegradability and hydrophobicity. The third is rejection. The microfiltration or ultrafiltration membrane has a marginal effect on the direct retention of TROPs. Some initial removal may be observed, but this is probably due to initial short-term physical adsorption into the pores. However, the adsorption and size exclusion by the gel or cake layer are non-negligible. The TROPs can be readily rejected when they are adsorbed in the sludge phase or bound to colloids. Lastly, a small portion of TROPs may evaporate under the aeration conditions in the aerobic or membrane tanks. The biological responses to the pharmaceuticals in wastewater systems are also noteworthy. Wastewater treatment plants, WWTPs, are potential reservoirs of antibiotic residues, antibiotic-resistant bacteria, ARB, and antibiotic-resistant genes, ARGs, and the release of these contaminants into the environment is considered to be risky to the ecosystems and human health. It has been reported that the MBR outperforms conventional activated sludge process in the removal of most ARB and ARGs, owing to the efficiency of membrane rejection. However, some ARGs still persistent in the membrane effluent, and further effort are required to achieve a thorough elimination of these substances. Microplastics, commonly defined as plastic particles smaller than 5 mm, have recently raised public concerns for human health and ecological safety due to their potential ecotoxicological impacts and persistence in the environment. These materials are difficult to settle in sedimentation tanks and, as such, have not been satisfactorily removed in conventional wastewater treatment plants. In comparison, the MBR can achieve over 99% removal of microplastics, owing to the evident superiority of membrane rejection. The membrane can serve as an effective barrier to block the discharge of microplastics from wastewater treatment plants into the environment. Nowadays, wastewater is regarded as a stream that contains valuable resources rather than just a contaminant, and energy and resource recovery from wastewater is a vital development aspect of a sustainable wastewater treatment system besides water purification. The anaerobic treatment process is technically promising to realize this goal, and the NMBRs are attracting lots of attention due to their advantages in retention of slow-growing anaerobes, excellent and stable effluent quality, efficient bioenergy production, their small footprint, etc. Anaerobic treatment technology is expected to achieve energy recovery. NMBRs enables methane energy recovery while water purification. To date, NMBRs have been successfully applied to treat high-strength wastewater with COD of 100 to 1000 mg per liter, with pollutant removal efficiency of mostly over 90%. With relatively low organic strength but a large water volume, municipal wastewater treatment has recently become a hot application field of NMBRs, and various configurations and modifications have been proposed to enhance the treatment performance and methane production. In general, NMBRs produce 0.1 to 0.5 cubic meter methane per kilogram COD removed or methane in municipal wastewater treatment. Methane production in AMBRs is affected by both operational parameters and the bacterial computation in the reactors. As for the operational parameters, the fermentation temperature, pH, and organic loading rate can significantly influence the methane production. For the fermentation temperature, the mesophilic 20 to 42 centigrade and the cyclophilic 0 to 20 centigrade conditions are favored for NMBRs, and higher methane yield was observed at higher temperatures. Besides, the neutral pH condition and an appropriate organic loading rate are also crucial parameters of biogas yield, and the theoretical optimal methane production of 0.382 cubic meter methane per kilogram COD removed was proposed at an organic loading rate of 6 kg COD per cubic meter per day for NMBRs treating municipal wastewater. As for the bacterial competition, it can also affect methane production. For example, if the organic load is insufficient and the sulfate content is high, the methane production will be affected due to the internal competition between sulfate-reducing bacteria and methane-producing archaea for organic substances. Currently, the NMBR technology is still facing some challenges, including methane loss and membrane fouling. The methane loss merely indicates the dissolved methane in the effluent. This phenomenon is temperature-related. Higher solubility of methane at lower temperature causes more methane loss, especially in hydraulic pressure-driven NMBRs. Correspondingly, harvesting the dissolved methane in permit is worth investigating from perspectives of both increasing biogas efficiency and reducing greenhouse gas emission. Besides, membrane fouling in NMBRs is also unavoidable. To achieve a steady operation of NMBRs, multiple fouling control strategies can be applied, including optimizing operational conditions, dosing additives such as granular activated carbon, increasing the shear force of the membrane surface by mechanical movement or biogas sparring, regulating chemical cleaning, etc. It should be noted that with further research and development, NMBR has a promising practical application to achieve efficient energy recovery from municipal wastewater treatment. As a summary, in this section, we learned about the removal performance of MBRs for ordinary pollutants and emerging pollutants. We also learned about the hygiene water qualities of the MBR effluent. At last, we learned about the development potential of MBRs in energy recovery. I hope you enjoyed this section. Thank you.